Okay, good morning again, everybody. I was told that in the lecture today, you covered other applications of integrals, namely arclengths, surface areas, centroids, and then probably next meeting you'll start with Pappus's theorem for volumes. So we'll look at some examples on that perhaps later today. I have worksheet number 4, a blank version uploaded in my website, but these are just a compilation of the problems from the calculus textbook because again, I'm not sure up to what level of difficulty you considered in the lecture, so I decided to stick with the ones in the textbook. So perhaps you can choose some exercises from here. But I got a couple of, or actually, I got a bunch of questions in the chat, probably about previous quizzes or homework, so I'll be happy to answer them first. Oh, by the way, we have started grading homework, the written homework you submitted last week. Um, it should be done by the end of this week. That's our deadline for grading it. Just for your information, 5 problems will be graded for just completion. So if you did a valid complete attempt to uh, to those 5 problems, regardless of whether you got the correct or wrong answer, you get 5 points. And then the other 5 questions will be graded for accuracy and how you solve the problem. So that would be worth 15 points each. So that would be 25 plus 75. The odd numbers in that written homework were graded for completion, and the even numbered problems were graded for accuracy. So you should be able to get your results over the weekend. Just a disclaimer though, the uh, the written homeworks were distributed to us randomly. So even if you're in my lab, there's no guarantee that I will be the ones that will be grading your work. So it would be a different TA. It can be a different TA that will grade your work, right? But there's a reconciliation period, perhaps until early next week. You can send me your questions why you got just this many points for this particular problem, and I can double check and then propose an additional points for you if the case merits. There would be partial points given to the even numbered problems, which are graded for accuracy. But for the odd numbers, which were graded for completion, it's either you produce a complete solution, or you attempted a complete solution or not. So that's all or nothing. So for those graded for completion, it's either 0 or 5. But for those graded for accuracy, it's 1 to 15 or 0 to 15 points. So there would be partial credits. That's why I encourage you to always include all the substantial parts of the solution so that you get as much partial credits as possible if you didn't get the entire solution correctly. Okay, so let me go to the first question sent. It was sent by Kingsley on the chat. Let's see. These are volume problems. I guess this would be a good. This will still be a good review about the things we talked about last time. So let's see. So for his first question, you guys can check it in the chat. He sent it. This is the first question. Um, so for the first problem, we need to find the volume of the solid bounded by the re, uh, the solid of revolution created by revolving a region omega, bounded by the curves y equals root x, y equals 0, and x equals 1. And for the first problem, the AOR is the y-axis. Okay. So again, the key here is to at least have a good idea of how the figure looks like. So have a good sketch of omega. So the first curve is y equals root x, so it will be a semi-parabola like this. And then y equals 0 is just the x-axis. That's y equals 0. and x equals 1 is just this. Okay. And then so the shaded region should be this. So this is omega. Okay. And then the key here is take note of the axis of revolution. The axis of revolution is the y-axis. So we are revolving around the y-axis. And then the next thing is to decide what type of strips to use. So it's up to you guys which one to use. I guess both horizontal or vertical strips are both useful in this particular case, because if you draw a vertical line or a vertical strip, it's going to be red versus the pink one all throughout the region. Or if you draw a horizontal strip, it will always be the blue versus the red curve. So no splitting of the integral is needed for either of the two cases. Now the problem is silent as to what strip to use. So you have the liberty to choose the type of strips that you want. Perhaps for this particular problem, I'll use, well, what do you want? I'll prefer vertical strips, just because the functions are given in terms of x, so I'll take advantage of that. So the volume now, I want to set it up using the variable x. So I need the bounds for x. X started here at x equals 0 and ended up here at x equals 1, right? So the bounds would be from 0 to 1. And then the strips, vertical strips, would be parallel to the axis of revolution, because the axis of revolution is the y-axis. So here I will be using cylindrical shells. Again, because the strips that I decided to use were parallel to the axis of revolution. So that means the integrand will consist of the formula for the surface area of cylinders. So it's going to be 2 pi radius times height. So in order to determine the radius and the height, I will draw a typical cylinder. So a typical cylinder that will be formed after the revolution would be something like this, right? So I know that the radius will be this length, right? But remember our convention, whenever measuring something from the y-axis to the right, that's always x units. So that means the radius here would be x units, because it is from here until here, that's x units, okay? And then 2 pi radius times height. So we need to determine the height of the cylinder. But the height of the cylinder is just this one, right? Which is basically the height or the length of the vertical strip. And it's going to be top minus bottom. It's going to be root x minus 0, right? And then you simplify, you can rewrite it as the integral from 0 to 1 of 2 pi x to the 3/2 dx. And then I think you guys can perform the integration over here. Okay. So I leave the integration to you guys. I trust that you can do it. So it's just the numbers that you need to work on. Okay. Now the second part of the question is the same region. Okay. Same omega, but this time the axis of revolution is the line x equals 1. Okay. So let me paste the region over here. Okay. And let me just erase this. This is still our region, okay, omega. But this time the axis of revolution is the line x equals 1. So we will revolve around this axis. Again, I'll take advantage of the fact that the given functions are given in terms of the variable x. So I'll insist on using vertical strips again. But again, nothing is preventing you from setting this up using dy, right? But if you use dy, you will have horizontal strips. So your strips will be perpendicular to the axis of revolution. So you'll do the disk or the washer method, okay? But again, here I'll take advantage of the variable x. The bounds would be from 0 to 1. Again, vertical strips are are parallel to the axis of revolution. So again, here I'll use cylindrical shells method. And for cylindrical shells, we need 2 pi radius times height into the integral, right? And then let's draw a cylinder in order to have a good picture of how these elements look like, right? So a typical cylinder will look like this, or half of a typical cylinder will look like this, okay? And then now the radius of this cylinder is this length. Oops. That's the radius of the cylinder. Well, how long is that radius? Well, from here until here, we know that's going to be x units. That's 1 unit. Okay. Because from 0 to 1, that's 1 unit. And then I know that from the y-axis towards an arbitrary point in space going to the right, that's always x units. Okay. But the radius we are computing is this. That's the radius. Okay. So looking at the picture, it is clear that the radius would be of length 1 minus x. Okay. And then the height will be the height of the vertical strip. So that's going to be root x again. Root x minus 0, but I'll just drop the minus 0. So you'll have this. And you just need to integrate this to get the actual volume. All right. Is that clear, guys? Any clarification with that? Okay.
No, that's good. Thank you.
All right. Let's look at other questions here. Let's see. Maybe I'll go to Muriel's question first before going through your question, Kingsley, because I guess you sent 3 in succession. So I'll skip over for now to Muriel's question. Okay, so here, Muriel's question, we need to sketch the region bounded by the curves. Okay, let's have the curves. So the region R is 2x plus y equals 2, 8x plus y equals 8, and x equals 0. And then we need to find the volume when this region is revolved around the y-axis. Okay. Now let's see. Usually it's easier to sketch the graphs if you write them in more familiar form. For instance, this curve can be rewritten as y equals 2 minus 2x. Okay. So if we will sketch that. We observe that that is nothing more but the equation of a line. So you just need to give a specific two specific x values. So you get 2 y values. Then you connect those 2 points into a straight line. Okay. So here 2 minus 2x, when x is 0, y is equal to 2. Say 2 is here. And then when y is 0, then x should be 1. So this would be the first curve. Okay. And then the second curve would be this curve. Let me rewrite it as y equals 8 minus 8x. So that means here when x is 0, y is 8. My figure is not drawn to scale, so I'll put just 8 there. And then when y is 0, that means x is equal to 1. So I have a point here. Luckily, there we discover a point of intersection. Okay. And then x equals 0 is just this, the y-axis. So the shaded region here would be this oblique triangle over here. Okay. And then you want to get the volume of the solid obtained after rotating this region R about the y-axis. So this would be our axis of revolution. Okay. Now again, I simply want to take advantage of the functions being given in terms of the variable x. So I'll use vertical strips here. Actually, horizontal strips would be more would be more messy here, because if your horizontal strip would be on top, it would be the purple line minus the y-axis, and if it's in the lower portion of the shaded region, you will have purple versus red line. So I won't set it up using uh, horizontal strips. So I'll stick with the vertical strips. Again, vertical strips require the variable x, and then the bounds for x here would be from 0 until 1, because you notice that the region started here when x is 0 and ended up when x is equal to 1. And then it's gonna be what type of cross sections do we have? Our vertical strips are parallel to the axis of revolution. So again, this is cylindrical shells. Okay. And cylindrical shells calls for 2 pi radius times height in the integrand. So let's determine what would be the radius. Again, it would be very helpful if you can draw how the cylinders look like, or half of them. So starting from the axis of revolution towards the top end of the horizontal of the vertical strip, that will be the radius of your cylinder. So the cylinders will look like this. Okay. That's our typical cylinder. And then let's measure the components of the cylinder. The radius would be from here until here, right? That's the radius. Well, the radius is something coming from the y-axis towards the right, and our convention says that's always x units, okay? From the y-axis towards the right, it's always x units, okay? When that point x is arbitrary. And then the height is nothing more but the height of the vertical strip. So it's going to be top minus bottom. So the top function is the purple line, 8 minus 8x, minus, don't forget the grouping symbol here, because the lower function consists of 2 terms. So we don't want to forget that that negative sign in front of the lower function should be distributed to both terms. So there would be a 2 minus 2x over here. Okay. Oops, and then oops. Okay, and then simplify the radical, the integrand, and then you should have an easy polynomial to integrate over here. Taylor, yes, you can use there are questions that are silent upon what method to use. So whenever that's the case, you can pick what method to use. You're right. Cylindrical shells method are always used as long as the cross section, or as long as the strips are parallel to the axis of revolution. Okay. But if the questions ask you to use the disc or the washers, then you should use strips that are perpendicular to the axis of revolution, and you should follow the instruction. I mean, in using the disc or the washer method. So yeah, those are the complications or the different dynamics of these questions. Yeah, you can use cylindrical shells for any type of questions unless you were specifically told to use the disc or the washer method. Because I guess for me, sometimes cylindrical shells are much easier than the washer method. Because for the washer method, you have outer radius squared minus inner radius squared, which might make the integral complicated. So my preference usually would be the cylindrical shells method, as long as I don't need to split the integral up. Okay, so let me see. Yeah, Muriel, I'll skip your other question just to give time to Herson's question. Okay. Let's call this question D. I guess this is problem 19 somewhere. Is it from your homework? Is it due today? Anyway, so Herson's question, we are given the region R on the first quadrant. So let's say on quadrant 1, bounded by f of x equals cx squared and y equals 2. And then AOR is the x-axis. And then the volume of the solid is given now. Wow, this is an interesting one. 64 pi over 5. And then you were told to find C. Anybody who got already this question? Or the answer to this question? Well, I see the difficulty here because the function f is given in terms of a parameter. So in your solutions, you set up everything, keeping C as a constant. Just keep in mind it is a constant, but we don't know what is its value for now, right? So we'll keep on working with C until we have the integral that gives us the volume and put that equal to 64 pi over 5. So let's see. Well, now let's do this. Have a sketch of the region. Cx squared. So I know that Cx squared is a parabola that opens either up or down, depending on the value of C, right? So if C is positive, the parabola will open up. If C is negative, it will open downward. So we don't know exactly what's happening here. But we were told that the region R, oops, sorry about that, that the region R is, did I lose my screen?
Your screen is off.
Yeah, my advisor is trying to call me, but anyway, he doesn't know that I'm in class right now, but hold on, yeah. Yeah, I have the do not disturb setting on. So anyway, so can you guys see my screen now?
Yes, we can see.
Okay, yeah. Or is it stuck? In my laptop, it's stuck. But anyway, so maybe you guys can see it. So now I'm thinking whether it's a parabola.
I think it is stuck.
Yeah, it's stuck. Let me try
Yeah,
this.
we only see the.
Yeah, on my tablet, I'm already on my. I'm already on the worksheet, but anyway, let me try again. Okay, there you go. So yeah, I'm thinking whether the parabola defined by the function f is opening up or down, right? Because I don't know the value of C. But there's a clue here in the problem that it says that the region R is on the first quadrant. So it's impossible for the function f to be a parabola opening downward, because if that happens, then there's no region on the first quadrant that could be bounded. So I'm guessing, or I'm thinking, okay, the parabola should look like this. But remember, I'll just remember that we are just on the first quadrant, so cx squared, okay? And then we have the line y equals 2, so y equals 2 is here, okay? And then this would be the shaded region R, okay? And then the axis of revolution is the x-axis, so we go over here. And then again, I'll take advantage of the fact that the functions are given in terms of the variable x. So I will insist on using vertical strips. Though here I will do the washer method. But anyway, that shouldn't be a big issue. So the volume will be given by an integral in the variable x. So we need to determine what's the starting x value and the ending x value. for sure the region will start at x equals 0 because it is on the first quadrant. So here's 0. The region will stop here at that point of intersection. So we need to solve for the POI. So we just put those two equations or those two functions equal to each other. So we'll have cx squared is equal to 2. So we see here that x squared is equal to 2 over c. Okay. So that means x is equal to plus or minus root of 2 over c. Good. But I'll take the positive root because we are on the first quadrant. So this would be root of 2 over c. That would be the upper bound for the integral. All right. And then the strips that we are using are perpendicular to the axis of revolution. So that means we will use the disk or the washer method. But if you draw a strip from the axis of revolution towards the end of the region, you will notice that some part of that strip is outside of the shaded region. So this is a washer problem, right? Or the cross sections that we have are washers. So that means here the formula would be pi times outer radius squared minus inner radius squared. So what would be the outer radius? Well, the outer radius would be this, the larger radius. So that's how many units? Do you agree that that's going to be 2 units, right? Because wherever I put the region, it's going to be the line, this line, y equals 2 on top, and y equals 0 at the bottom. So that's 2 minus 0. So that would be 2 units. So the outer radius is 2 units, quantity squared, minus inner radius squared. Well, the inner radius will be this height over here, okay? But that would be what? That would be the parabola versus the x-axis. Still top minus bottom. So that's going to be cx squared minus 0, right? So this will have a square over it, okay? And we know that this, when evaluated, should give us 64 pi over 5. Okay. So what we'll do here is, okay, let's simplify the integral. 0 to root 2 over c of pi times 4 minus c squared x to the 4th dx equals 64 pi over 5. So what you need to do here, guys, would be to evaluate this integral, okay? But keep in mind that c is a constant, okay? And then what you'll get here is an expression involving c. Then you put that equal to 64 pi over 5, and then all you need to do is to solve for c.
I have a question. Why do you put it from 0 to square root of 2 over c?
Oh, good question. Because there, remember that the bounds would be the bounds for the region. So you see that the region started here at x equals 0, okay? And it will end here at this x value, which is basically the point of intersection between the parabola and the line. So to find exactly what is that x value over there, I put cx squared equal to 2. And then I just solve for the x value there. I hope I did the algebra correctly. I think so. And then, so this would be your POI. Okay. Is that clearer now? So basically, that's the x component of the point of intersection. All good?
Yeah.
Okay.
Okay.
Now, all right. That sounds good. Let's see. There's still a couple of questions in the chat, though. I guess. Let me just see. Kingsley's question would be, well, I guess they are related to finding volume. So I guess I hope the 4 examples that we had today will help you with those particular problems. So if you still find difficulties on those ones, I'll be happy to help you during office hours, or if we'll have time later today. I want to go into quick examples about what you went through the lecture today. So yeah.
Yeah, that's fine.
Okay. Though any particular problem on those any particular difficulty with those problems?
Just a little bit, but honestly, she moved the quiz date back to Wednesday, so if I still have issues with them, I'll bring them up in the next lab on Wednesday.
All right. Yeah, just because I want to cover a couple of examples for what you did in the lecture today, so that will not fall too far behind. Or
Yeah.
if you also want, I'm on CASA. My tutoring hours are 6 to 7 p.m. every Tuesday and Thursday, so you can also drop by there.
Okay.
Also, all throughout the days, there are tutors available in CASA. I guess you are receiving notifications whenever a tutor comes online. You can also check your team's calendar. You're added to the CASA online Math 1432 tutoring team. So if you check your calendars, you'll see there whenever there's a TA that goes online for tutoring. So you can also ask help there whenever you're not free during my office hours. All right?
Okay, sounds good.
Okay. Yeah, but let's see if we'll have time later today. So in the lecture today, so you started talking about, or you talk about finding the arc lengths, surface areas, and centroids of plane regions using integrals. So let me go here. So let's start with arc length problems, and I guess this is pretty straightforward. All you need to remember is the formula. So I hope the principle behind this formula is clear now. I suppose this was discussed in details during the lecture today. So the thing here is that if you have a function f that is continuous over the interval AB, so this notation is just a shorthand for me writing f is a continuous function over the interval AB, then its arc length over the interval AB is given by I'm not sure what your notation for the arc length is. I'll just use capital L. It will be just the integral from a to b of the square root of 1 plus the derivative of f quantity squared dx. Okay, and there's an analogous formula if your function is given in terms of y. You could have done integral from c to d of the square root of 1 plus the derivative with respect to y quantity squared dy. So that's perfectly fine. Let's solve some examples. Though I really think these are straightforward ones. Unless you have specific difficulties with this or any specific question regarding this. Because usually students sometimes would like to skip this one because they think this is quite easy. But anyway, so let me try some problems from the worksheet. Let's try problem 8. So for problem 8, we need to find the arc length of this function over the given interval. So the function is f of x equals 1/8 x squared minus ln x over the interval pi over 6 to pi over 3. Sorry, from 1 to 5. I'm looking at the other problem. Yeah. Okay. All right, so looking at the formula here, it's straightforward. All you need to do is find the derivative, square it, and then put it inside a formula. So let's start by looking at f prime. I hope you still remember how to do differentiation now. Sometimes it might get confusing between derivatives and integrals. But anyway, this will be what? X over 4 minus 1 over x. Okay, that would be the derivative. So all we need to do is plug this into the formula for the arc length. So the arc length would be the integral from a to b of the square root of 1 plus the derivative squared. So that's x over 4 minus 1 over x quantity squared dx. And that's it. If you want to have the exact arc length, then all you need to do would be to evaluate this integral. Oh, sorry, the bounds are not a to b. I know exactly what a and b are. This would be 1 and 5 respectively. Okay. I don't think you will have a hard time doing this. So, okay, let's just try another one. Probably problem, let me see. Just let me know if you have questions on this.
Yeah. So for when if they want us to solve for arc length, we don't have to like continue solving. We just leave it like this in the integral form.
Oh, it depends on the instruction. Let me double check the instruction here. If you were asked to just set up the integral that will give you the arc length, then this is fine. But if you were told to find the arc length, then you need to evaluate this integral.
Okay.
Yeah, let me just see. Problem 8. Oh, this asks us to find the arc length of the graph over the indicated interval. So I suppose we need to technically find a value. So we need to end up with a constant here. So I leave you guys the integration over here. Will that be hard? I don't think that will be hard. You just need to expand this out, multiply it by itself, or use your formula for squaring, add 1 to it, then put a square root. Perhaps you will use a u substitution over here. So I'll insert the final answer later, but the emphasis here would be on setting up the integral rather than computing the integrals themselves, because I hope that is now clear from Calculus 1 or the first few weeks of Calculus 2. So the focus really here is on having the right setup for the integral, because after that, all that follows would be calculations that we have covered before. All right. Okay, let me take a look at another one. Let's say, oh, problem 18 looks complicated. Let's see how that goes. Problem 18, x equals beta y minus 4 over 9 beta squared to the 3 halves, where y is between a and b. Okay. So I guess this will look very intimidating if you will just be looking at it. But if you try to analyze it, we just want to find the arc length. And the function here is given in terms of the variable y. So you can imagine this to be your g of y. Okay. So this messy expression here is your g of y. And beta is not a variable in this problem, because we only expect the variable, we only expect y to be the variable in this function. So beta is just a constant. So note, beta is just a constant. We just don't know what its value is, but it's a constant. So the only variable in this function would be the variable y. Okay. And then we know the bounds. We want the arc length for y being between a and b. So here the formula remains the same. The arc length would be the integral from a to b, but this would be an integral with respect to y, because our function is given in terms of the variable y, but the formula is analogous to that whenever the function is given with respect to x. So this would be the square root of 1 plus g prime of y quantity squared. Okay, so that tells us, oh, I just need to find the derivative of g and then move on, right? So here, g prime of y, the derivative of g with respect to y is what? Okay, first term. We have beta y. The derivative of beta y is simply what? That will just be beta. Oh, sorry, this is raised to the 3 halves. I forgot about that, raised to the 3 halves. So it's not as simple as what I thought. Okay. So here we have something raised to the 3 halves. So its derivative would be 3 halves beta y minus 4 over 9 beta squared raised to the 1/2. Okay. Then chain rule kicks in, times the derivative of the inside function. But the derivative of the inside function is simply beta, right? Because if I take the derivative of the inside function, the derivative of beta y is simply beta. And the derivative of 4 over 9 beta squared is 0. Because that term there is just a constant. Remember, beta is just an unknown constant. Okay? So I guess that's it. Maybe you can rewrite it as 3 beta over 2 times beta times the square root of beta y minus 4 over 9 beta squared. Okay, but remember what goes inside the formula for the arc length is the derivative squared. So the square root will be gone. I guess we will just have one outer square root here. So what we'll have would be the integral from a to b of the square root of 1 plus the derivative squared. So I need to square this derivative over here. So that's going to be 9 beta squared over 4 times beta y minus 4 over 9 beta squared dy. All right. And then let's see if we can simplify this further. This would be the integral from a to b of the square root of 1 plus, here we'll have 9 over 4 beta cubed y minus 9/4 beta squared times 4 over 9 beta squared. That will just be minus 1 dy, right? So there I distributed 9 beta squared over 4 over both terms in that factor. Good. And so this will just be the integral from a to b of the square root of 9/4 beta cubed y dy. And then since we are asked to evaluate, to find the arc length, so I need to keep on simplifying this until the integral would be gone. So, but I could free some things up from the square root. So we can have a 3 over 2 here, and then beta to the 3 halves times y to the 1/2 dy, right? And then notice that 3 halves, beta to the 3 halves are just constants, so they go out of the integral. So we will just be integrating y to the 1/2 dy. And remember, this will just be what? 3 halves beta to the 3 over 2 times integral of y to the 1/2 is y to the 3 halves all over 3 halves. Evaluated from a to b. And then I can take care of the 3 halves here. That will become a 2/3 in the numerator, but I have a 3 halves earlier. So they will sort of cancel each other out. So we'll just have beta to the 3 halves evaluated from a to b. So basically the final answer here would be beta to the 3 halves times b to the 3 halves minus a to the 3 halves. Okay, and that would be the arc length. So unfortunately, the problem did not give us the value for beta, nor the values for a and b. So we'll keep the final answer this way. Okay. How about that, guys? Any question? Are you guys still there? Okay. Do you think there would be a difficulty with arc lengths? I guess these are pretty straightforward problems. So can we move on to surface areas? But don't worry. Again, if you find some interesting or some difficult problems from the quizzes or the homeworks, you can send them to me next meeting. But I guess the point of today's meeting, since you just discussed these things, is just to have a clear understanding of the process. And then from there, you can try problems to build up your confidence or your proficiency in answering these types of problems. Okay. So I guess that that is quick. Oh, any question? Okay, I thought somebody's gonna unmute him or herself. Okay, let me go to look at surface areas. Well, for the surface areas, for surface areas, let me start on a new page. Okay, the formula for the surface area of a solid of revolution is this. It will be an integral from, say, A to B times 2 pi times the arc length. Or actually, not the arc length itself, but the formula we had for the arc length. Oops. Basically, 1 plus f prime of x quantity squared dx times some radius here. I'll let you know what that radius is later, but this is the general formula. Let's probably draw a picture to see how this works. Okay. So suppose we have a region over here. Okay. This is A, this is B. So, sorry, not a region, but just an arc. Okay. So suppose we are considering this red arc over here. And we want to revolve it around some axis. So say this is our AOR. Okay. So imagine what will happen. So we are not revolving a shaded region with respect to the AOR, but we are simply revolving an arc over the AOR. So if we do the revolution, can you imagine what happens? What we will have is not a solid, but just a surface, because everything in the middle would be hollow, or it will be empty space, right? Because we don't have a region to revolve around the axis. So what we will form instead of a solid is just a surface. You will have a boundary, but it would be empty inside. So that's why we don't compute for the volume, because the volume will be 0, but it will have a surface area, right? But what would be that surface area? Well, that surface area will depend on two things. First thing is the length of the arc, because basically that gives us one of the dimensions of the surface of revolution. And that's why you will see the formula for the arc length appearing in the formula for the surface area. Because if you imagine we forming the region over here, that will sort of give us the height, right? The length of the arc length will give us one of the dimensions of the surface, right? But what remains would be to see, remember what will happen. This will revolve around the axis of revolution. So I hope you can imagine what happens. But essentially what happens is that this arc is being rotated or revolved around the axis of revolution with what would be the circumference, because this will go that way circularly over there. So this is what will happen when we do the revolution. So basically that length will travel some amount of distance in space. But how much is that distance? Well, the distance would be exactly the circumference of this circle that I have just drawn. And that's why you have a 2 pi radius here, where 2 pi r accounts for the circumference or the distance traveled by the arc, which we know to be along the circumference of a circle, because we are rotating it exactly over with respect to an axis of revolution. But what is the circumference of this circle? So we know the formula for the circumference of a circle is 2 pi r, right? And that's why you had that 2 pi r inside the integral, okay? Now, what is r? R is the radius of that big circle that was used in revolving the arc length. But if you want to measure that, that will just be the distance between the arc and the axis of revolution. That would be your AOR. And in this case, sorry, not AOR, that would be our R. This would be R. R is the distance from the arc towards the axis of revolution. So it will just be top minus bottom. So usually you will have f of x over here and say this is y equals, say, c. So the radius r would be top f of x minus the bottom, which is equal to c. So you will you need to compute how long is the arc is from the axis of revolution. Okay. Unfortunately, we don't have time now. Maybe I'll start with a couple of examples about the surface area next time. But I guess I hope you get the picture. What I'm trying to drive at here is for you to understand how the formula for the surface area came about. So it's basically the circumference, which is the distance traveled by the arc, times the arc length. So that it would be clearer for us when we go next time into solving these problems, because we can interpret this by looking at the figures involved, right? So we know exactly what the radius would be of that circumference and what would be the arc length, okay? So I guess this is a good time to stop. So yeah, I uploaded the worksheet number 3. So you can try some problems over there. But if Dr. Almus will send us a specific material, then I will edit worksheet number 4 and probably call it worksheet number 5. So I'll just let you know what worksheet we'll be working on Wednesday. All right. Okay, guys. Yeah. Enjoy the rest of the day, and then see you Wednesday. Bye.
Thank you. Have a nice day.
Mm-hmm.